We explored methods for managing groups and centers of rotation and scaling in an animation sketching tool. Our aim was to let animators work quickly and to keep animations simple as they were edited, no matter what strategy animators used. Our investigation was conducted around K-Sketch, which we modified to support keyframe interpolation in addition to real-time performance. These modes can be mixed arbitrarily. Here, an animator holds the control key to perform a translation, and then rotates the object without holding control to add an interpolated rotation. Note that editing updates both performed and interpolated motions in the same way. As in the original K-Sketch, performing a rotation or scale on an object that is already moving will cause a ghost to appear, so the animator can manipulate it in one place. Note also that translations appear as blue motion paths, rotations as green paths, and scales as red paths. As part of our investigation, we implemented two grouping methods. Manual grouping mimics the behavior of conventional tools like PowerPoint, while automatic grouping has the more flexible behavior found in the K-Sketch animation sketching tool. What happens when these grouping methods are used to make this animation? With manual grouping, users' experience depends on their grouping strategy. Here are two examples. On the top, the animator ignores grouping. On the bottom, he groups whenever possible. When aggressively grouping, the flow of action is interrupted by the need to group objects. Ignoring groups clutters the interface with separate motion paths for each object. When the time comes to break off part of a group, an ungroup action causes the group's motions to be lost. These motions must be added again to restore the animation to its previous state. The scenario concludes in a similar way, with added interruptions when grouping aggressively and added clutter when ignoring grouping. With automatic grouping, grouping strategy does not matter. The scenario proceeds without clutter or interruptions. Our investigation also led us to implement three methods for handling object centers. Same center mimics common tools like Flash, where all of an object's motions must have the same center. The other methods allow centers to change. Different centers has no restrictions, but refactored centers has two restrictions discussed later. Let's see how the same center and different center methods affect this scenario. Same center is on the top, and different centers is on the bottom. Both methods start with moving the center and rotating. Same center must erase the block and paste a copy every time the center moves, after which the scenario continues normally. Refactored centers handles this scenario much like different centers. We pause now to describe the restrictions enforced by the refactored centers method. First, motions at the same time must have the same center. Second, the center must stay inside the object's bounding box. Refactoring occurs when motions violate one of these restrictions. Let's now compare the refactored centers and same center methods as an animator edits keyframes for this animation. Same center is on the top, and refactored centers is on the bottom. The animator first turns and moves the arrow to the bottom block. Then he moves the center to grow the arrow from its tip. In the same center method, this shifts the rotation motion to a new center, and the animator must repair the motion. The refactored centers method instead detects that the scale uses a different center. It then refactors the old rotation into a rotation about the new center, plus a correcting translation, so it moves just like it did before. As editing continues, the two methods are nearly indistinguishable. Different centers handles this scenario with no surprising effects, because it puts no restrictions on centers. Finally,
Let's compare different centers and refactored centers as an animator rotates a star about a black hole. The same center method cannot do this.
Different centers is on the top, and refactored centers is on the bottom. Both methods start with performing a pulse motion on the star. Then the animator rewinds, moves the center, and performs a rotation. Both methods produce identical motions, but on the bottom, the rotation is refactored because the center was outside the star's bounding box. On the top, different centers causes the rotation center to move erratically. This is a consequence of our data model, as explained in our paper. We evaluated these grouping and object center methods by showing video prototypes like these to animators and collecting their reactions. Thank you for your attention.